All right, good morning, everyone. Today is Tuesday, August the 31st. We are starting day one of three, I believe, of 1.05. Yep, there's 3 days. This is a 3-day lesson. So you don't have to do your quiz on 1.05 until I think Thursday, right? Yep, Thursday. So all of you should have 1.02 and 1.03 quiz done. We're starting 1.05 today. The rational root theorem. So we're going to determine all possible rational roots of polynomials. Make sure you have your paper, pencil, and definitely a calculator. All right, so you're going to hear me use the terms roots, zeros, x-intercepts, solutions. All four of these words mean the exact same thing. That is very important to understand when we go, well, this entire term, really. You're going to hear me use these terms interchangeably. You'll hear me say roots, you'll hear me say zeros. I might say x-intercepts if you're talking about a graph. I might say solutions instead of roots or zeros, but when I say one of these four words, they all mean the same thing. Is that clear? All right, just want to make sure. Again, roots, zeros, x-intercepts, solutions all mean the same thing. All right, so the fundamental theorem of algebra. I don't know if you, well, if whenever you all go to the modules and you work through this and read through their examples and what they have, they're gonna have the definition of, well, this right here, which says every polynomial equation of degree n with complex coefficients has n roots in the complex numbers. Well, that sounds super confusing, because it is. So the degree n, this is talking about your leading term, which would be this right here. This is the nth degree. So this could be, it's always, remember, it's always descending order, right? So the highest will always be first. Or at least it should be if it's written correctly. So if that was a 4, this would be a 4th degree polynomial. If that was a 8, that would be an 8th degree polynomial. If that was a 2, that's a 2nd degree polynomial, and so forth. Now, what in plain English, what this is telling you is that degree determines how many solutions or how many roots or how many zeros you are going to have. So if that was x to the 3rd power, you would only have 3 solutions. If that was x to the 5th power, you would have 5 solutions. No more, no less. So that's all that is saying, and just lots of fancy words, right? So whenever you see, we work on these problems in this, well, in this unit, this section or future sections, you can look at a polynomial that we're trying to solve our solutions for, and the leading term, the power determines how many solutions you're going to have. Also very important to understand. All right, so let's apply the fundamental theorem of algebra. All right, we want to write a polynomial function whose zeros are -3, 1, and 4. Again, we want to write a polynomial that has these 3 solutions, these 3 x-intercepts. If I was to graph this, and I just have that, I'm not actually going to use it on this problem, but if I was to plot these, it would cross the x-axis at -3, which I think is about right here, at +1, and at +4. Right there, right? So think back. So I'm pretty sure you may have done this in Algebra 2. Now, we kind of did it this last week and maybe yesterday a little bit. When you're given solutions, now think about synthetic substitution. When you're given solutions to plug in, how do we write the factored form, the binomial? So what would the binomial of this first one be? Any ideas? Solution is -3. What would the binomial be? Noah's correct. X plus 3. Nice job. Good job, Camille. So when given the zeros, the factored form is just the opposite, right? So the first one would be x plus 3. What's the second one going to be if the solution is a 1? X minus 1. Very good. And the third one, if the solution is a 4, what's the binomial? X minus 4. Very good. And then we just set it equal to 0. Or set it equal to f of x. You say f of x is equal to this binomial times that binomial times the last binomial, right? So you'll see you'll see the module. They'll set the answer either equal to 0 or equal to f of x. It means the same thing. All right. So are everyone great on how we found the binomials based on the given solutions? It should be pretty straightforward, right? Given the solutions, in the binomial form right here. If you think about it in algebra 2, if once you have it in factored form, setting the factors equal to 0 and solving will get you back to here. Ooh, wow, right? Awesome. You're like, well, yeah, no kidding. We already knew that. Let's keep going, right? All right, so we want to simplify this. So in chat or on mic, what should we do first? What's our first step to simplifying? What's the operation we're going to do? Multiply the first two binomials. Yeah. So we would do x plus 3 times x minus 1. So somebody in chat said, or Noah said, multiply the first two. Now, what's the property of multiplication? The associative property, the cumulative property of multiplication, I think it's called. The order at which you multiply does not matter. So if you wanted to multiply x minus 1 and x minus 4, if you want to multiply these two binomials first, you can. I could do x plus 3 times x minus 1. I could do x plus 3 times x minus 4 first. It doesn't matter, but let's keep it simple and let's just do the first two together. So how do we multiply the first two binomials together? What do we do? What's the acronym we use to multiply binomials? FOIL, yeah. FOIL, first, outer, inner, last. So everyone multiply your first two binomials together. Do x plus 3 times x minus 1 by using the FOIL method. All right. Before combining like terms, and you did the first, outer, inner, last, what did you get for the for the four terms here? What did all of you get before combining like terms? What did all of you get? Got x squared, a negative x, a positive 3x, and a negative 3. I think I would agree with all of you. Yeah. X times x is x squared. X times negative 1 is negative x. 3 times x is 3x. And then 3 times negative 1 is negative 3. And then we'll just carry down the x minus 4, right? What terms combine in here? What can I combine together? I'm asking really basic questions. The x's. And when you combine those x's, what do you get? What is negative x plus 3x? 2x. Yep. Just want to make sure that we all know how to combine like terms. All right. So everyone doing great on how we get to this step so far. This is all basically algebra 1 math, I think, right? All right, good. All right. Now we got to multiply this trinomial times this binomial, right? So everyone quickly do that. I'm going to give all of you, I don't know, how about a minute, right? A minute, I think it should be okay. multiply this times this. So, hopefully that all of you are tabbed into this and working this problem out with us. Like I said, there's no point of coming to a live session unless you're actually going to participate. Why log in and not do anything when you can just watch the recording later, right? So make sure all of you are actively participating and working these out with us. All right. What did everyone get? After you multiply them out and you combine like terms, what did you get? X cubed minus 2x squared minus 11x plus 12. Looks like two people wrote that. So I will go with the majority. One person had 5x instead of negative 11x, and they have a minus 12 instead of a positive 12. All right, looks like most people are agreeing on the first two that somebody posted. So let's take a look. Got x cubed for the first one, minus 2x squared for the second term, minus 11x, and then plus 12. So let's see how we got there. Oh, you didn't combine, but I just did. Okay. All right, so x times x is x cubed. X squared times negative 4 is negative 4x squared. And then, so let me use my pointer here. So we did x squared times x is this. X squared times this is this. Now we go to the 2x. 2x times x, 2x times negative 4. So 2x times x is 2x squared. 2x times negative 4 is negative 8x. And now we go to the negative 3. Negative 3 times x and negative 3 times negative 4. And that's how we get these two. So nice job, everyone who got that correct. All right, so this means, well, you want to combine like terms, which we did. We skipped a step just to show what everyone got. Combine like terms, x cubed carries down. We have x squared and x squared. So negative 4 plus 2 is negative 2x squared. We have negative 8x and negative 3x. So negative 8 minus 3 is negative 11. And then you just have a constant of 12 by itself that carries down. So, just a quick little refresher on combining like terms. All right. So that means the question says, what is a polynomial function of least degree? Well, so this right here, we are done. That is the answer. So I'm just going to write it, just highlight it to show that's my answer. So, make sure on your TGA, make sure you box or circle your final answer. Don't just give me a bunch of work. So give me a bunch of work and not actually like identifying what your final answer is. I can't give you credit because I don't know that you know what the final answer is. You just have all this work. Keep that in mind, okay? And of course, no work, no credit. Definitely no work, no credit. You go right to an answer, I'm going to say, all wrong. Is changing font color. Okay, so it depends what color. So I'm colorblind, so it's hard for me. Like red and blacks, I have a hard time seeing the difference. Don't use yellow and green. I have incredibly hard time even seeing those colors, especially if they're light. Blue, so if it's dark blue, see dark blue and black also look the same to me too. Just box your answer. Or highlight it, right? I can see if you highlight something, I can see that. I tell you what, if there's any issues with your submission, I will put comments on there and you can fix it. How about that? All right. So before we go on, And this is, I want to say this is probably review from Algebra 2 sometime. How's everyone feeling about given zeros and putting it all together to create your polynomial? Pretty straightforward, right? All right. So I don't have another example on this just to save time. I want to go to the harder stuff. It looks like all of you are pretty good on this. All right. The rational root theorem. This is brand new stuff. This is, it's called a PQ list. A PQ list. So let me back to this problem here. Let's say I gave you this problem and I said, what are the zeros? Well, we all should know how to factor a polynomial if it's a second degree polynomial, meaning like, let's say I didn't have this x cubed and this negative, and I just had 2x squared minus 11x plus 12, for example. We should all be able to factor that, right? But given a polynomial like this with that's a third degree polynomial, and I said, hey, factor this, well, this isn't so easy. Or let's say if it was a fourth degree or a fifth degree polynomial, that's also very, very difficult, right? Well, creating this PQ list generates a list of possible real solutions. Remember, solutions, zeros, x-intercepts, forget one, roots, all mean the same thing. All right, so given this polynomial, all possible, now I underlined the word rational roots can be found by dividing all the factors of the constant term a sub 0 by the factors of the leading coefficient a sub n. So in other words, it's just saying that you're doing your p value, right? The constant, your p value divided by your q value, which is the coefficient of your leading term. So 8 divided by 5. And like this says right here, don't forget, it's plus and minus. And that's why it's over here in the little theorem box. Yeah, it's plus or minus p divided by q. There's your p, there's your q. It's that easy. So rational roots. So this means solutions that are fractions or integers. This PQ list does not include possible answers that might be imaginary, so involving I. Keep that in mind. These are only real rational roots. So let's see how all this works. All right, identifying the P's and Q's. So, all right, class, what number is your P value? Go ahead and write it in chat. What number is your P value? Yes, your P value is the 6. And what's the Q value? All right, Q value is 3. So just remember the P is at the end, the Q is at the front. Makes you wonder why they don't call it a QP list. I don't know. They call it a PQ list. So it's P is at the end, Q is at the beginning. Don't mess that up. All right, so now what we're going to do is we're going to write your P value on top and your Q value on the bottom. Again, don't forget plus or minus. Every solution that we're going to write will have plus or minus. That is a given. All right, now, this step, we want to write all of the factors of your P and Q. So think about it. Let's do the easy one first. Let's do 3. What are all the factors of 3? Go ahead and just write it in chat. Emil says 1 and 3. And of course, don't forget plus or minus, right? Yeah, don't forget plus or minus. That's a given. So yeah, 1 and 3. Oh, plus or minus 1, plus or minus 3. Okay, good. All right, now think about this. Now, what are all the factors of 6? So we got, Rachel says 1, 2, 3, and 6. Did we forget any? I don't think so, right? Yeah, 1 goes into 6, 2 goes into 6, 3 goes into 6, 4 doesn't, 5 doesn't, 6 does. So it's 1, 2, 3, and 6. So we're going to write all of the factors. Yeah, he said 1 and 3. I don't know why I did individual boxes. 1, 2, 3, and 6. And it's usually easier to put them in order, least to greatest. I encourage it. I think you'll less likely make a mistake. All right. So it's very, very important to write all of the factors like I have here, and of course, plus or minus. Now, the fun part. Well, the long part, but it's not difficult. Now we have to create all of the combinations of this fraction. So for example, we're going to have 1 divided by 1. We're going to have 1 divided by 3. We're going to have 2 divided by 1, 2 divided by 3, 3 divided by 3 divided by 3, and so forth, right? Don't forget plus or minus. So 1 divided by 1, 1 divided by 3, 2 divided by 1, 2 divided by 3. What's the next one? 3 divided by 1. What's the next one? 3 divided by 3. What's the next one? 6 divided by 1. What's one? 6 divided by 3. So, is it pretty clear of how we go through and we generate our list based on our factors? Right. And guys, honestly, make sure you're paying attention this entire time, because after this page, I'm really going to explain some like really deep math stuff that might make you kind of say, "Aha, that's really cool." All right. So we generate this. Now we need to reduce all of our fractions, right? We have to, 1 divided by 1 is 1, 1/3 is 1/3, 2 divided by 1 is 2, 2/3, 3 over 1 is 3, 3 over 3 is 1, 6 over 3 is 2. So we need to simplify all of the fractions, and that's what I'm doing here. I feel like this is one of your TGA problems. Let me just double check. You all might be really curious of what. Let me just double check to see if you want a problem on your TGA. Oh, you actually. I don't good. I should have, right? I should have. Maybe I'll change my PGA problem. I don't know. Look it up. It's good. Next, we need to stop right by and circle you can't. So we're gonna have 1. I'll just show them all. We have 1, 1/3. We carry that down. We have a 2, 2/3, 3. We already have 1 written, so we skip it. Carry 6 down, and then we already have
Mr.
2
J?
over here. So
Mr. J?
this 1 and this 2 are duplicates. You don't write them again.
Mr. J,
This
you lagged
is
out.
your PQ list.
Mr. J, you lagged out a lot. So can you go back a little bit? If you can hear me.
I hear you. Go back where? I lagged for everyone? Oh no. Uh-oh. All right. So let me start over of where I think I lagged out at. All right. So once you generate the list, we want to reduce all the fractions. We did that here. Then from here, we want to write all of the generated PQ list, but no duplicates. So 1, 1/3, 2, 2/3, 3. 1 we already wrote over here. 6, and then 2 we already wrote over here. So no duplicates. Oh, I like that I'm talking about. Okay, so I checked TGA to see if we actually had a TGA question on this, and we don't. I thought we did, but we don't. What do duplicates say about the graph? Nothing. Nothing. So when you create your PQ list, just because you have duplicates doesn't imply anything about the graph at all. Why no duplicates? Well, because you don't need to write it more than once. Yeah, just because your PQ list needs to have unique numbers. There's no reason to have duplicates. Now, with that said, even though we create this list and we only write the numbers one time, because we only want a list of unique numbers. Just because it's only listed one time, it is very possible that our polynomial could have 1 as a root 2 times. Like we could have x plus 1 and x plus 1. So just because you only see it one time in our list doesn't mean it's a 0 one time, if that makes sense. Okay. So yeah, so just why no duplicates? This is how we do it. So if these are possible rational roots, will not all of the roots be solutions? Yes, that's correct. So this is a 3rd degree polynomial. How many zeros will we have at most? How many zeros? How many solutions will we have? 3, right? Everyone can see that it's a 3rd degree polynomial, so we could only have at most 3 solutions. Now looking at this list, 1, 2, 3, 4, 5, 6, and then plus or minus. So we have 12. We have written out 12 possible solutions to this, but we only have a maximum of 3. So most of them won't work. So think of a way that how can we check these answers? Before I give you the answer, how can we check to see which ones actually work? Yes, synthetic division. So synthetic division, or you could plug it in, right? I think synthetic would be easier. But yes, you could plug it in or do synthetic. Yep. So if you plug them in, you should get 0. Yeah. So yeah, if you plug them in, if you get 0, it's a solution. If you do synthetic division or synthetic substitution, you should also get remainder 0, right? And that's how we're going to check in the next few pages. All right, so I kind of probably said most of these bullet points already, but this list is just possible roots if they even exist. So it is actually possible that we create a list and none of them work. I guess that would be yeah, that would be possible. Very possible that none of them work. And in that event, it's because all of the solutions to that polynomial would be imaginary. But for just for your sake of your sanity, all the examples that you're going to have, at least one of them will work. If one, so out of all of these, the three solutions we have, at least one of these would work. All right, so other roots could include irrational or even complex roots, so like imaginary numbers. Irrational would be ones that involve like square root of 2 would be considered irrational. So how do we know which ones actually work? Well, we have to either plug it in or use synthetic division. So yes, this is very tedious. Can you imagine going through 12? So we create synthetic division, right? And we do it 12 times. How tedious is that? I feel like the words in math, when I say the words tedious and annoying, they kind of mean the same thing, right? How annoying is it to do all 12 checks? Very tedious, right? I know, dot, dot, dot. Yeah, my thoughts exactly. All right, so make it as easy as quick as possible, either direct or synthetic solution. I think Camille said this way, either you plug it in directly to see if you get 0, or someone else said use synthetic substitution and see if you get remainder 0. So either way work. There is one possible solution, the fundamental theorem of algebra. It states the number of roots of polynomials exactly equal to the degree. So we already said this. So this third degree polynomial, we're going to have at most 3 solutions. That's what this bullet point is saying right here. Oh, I state that right here. So if you happen to get lucky and you check 3 numbers in a row and all 3 check out, stop working. You found all 3. We know we need 3. If you find all 3, stop. There's no reason to check the rest of them, right? Now let's do that. All right. So this is the problem we've been working on. This was our PQ list that we created. I went ahead and I wrote out 1, 2, 3, 4, 6. I did 7. Okay, I did 7 of the 12. All right. So I'm just going to just quickly just show this. All of you by now should be pretty much experts at synthetic substitution or synthetic division. Remember, when you use synthetic division, we are checking to see if we get remainder 0. Remainder 0 means it is a factor. If you do not get remainder 0, it is no, it's not a factor. So we checked 1 here. We did the synthetic. We got remainder 21. So that means this is a no, it is not a roots. We go to the next one and we check that one. And we find that also doesn't work. And we go to the next list. Now, so generally speaking, if I was to do this, I would probably do the fractions last. I would do 1 plus or minus, 2 plus or minus, 3 plus or minus, 6 plus or minus, in hopes that I find all 3 solutions before getting to the fractions. But that may not always work. I went ahead and just went right to the fraction right now. So I did 1/3. So I will run through the fraction one real quick because we haven't done one in class, but same idea. Drop the 3. 1/3 times 3 is 1. 7 plus 1 is 8. 1/3 times 8 is 8/3. 5 plus 8/3. Now, I don't expect most or any of you to do this in your head. Type it in your calculator. 5 plus 8/3. Hit enter. We want a reduced, simplified, improper fraction, which is 23/3, if I did my math right. Hopefully these numbers are right. Then 1/3 times this fraction is 23/9. 6 plus 23/9 is 77/9. Definitely not 0, so it doesn't work. We all love fractions, right? Go back to the previous page. Sorry, I just read. Elizabeth, you want me to go back to this page? Okay. Let me know when you're ready. How about now? Right. And then we go to the next one and we check. And we get a no here. This one's nice because when we do the math, negative 1/3 times 3 is negative 1, 7 minus 1 is 6, negative 1/3 times 6 is negative 2, 5 minus 2 is 3, negative 1/3 times 3 is negative 1, 6 minus 1 is 5. So even though we had a fraction out here, we were able to keep everything in integer, which is nice. Makes the math simple, right? But still, doesn't work. All right, then we go to the next one. We go to 2. So we'll do 2, then negative 2. So let me oh man, so we are 0 for 5 so far. Then we go to negative 2. Ooh, that one worked. Thank goodness. So we found one. So we found one of the 3. And we do the next one, and so on. So at all the ones that I checked so far, so it was at 3, 6. So out of the 7 of the 12 choices, only one of them worked. So the reason why I said and so on and I didn't show the rest, because I know for a fact the remaining, the remaining 5 do not work. I just didn't show it. So even though we should have 3 solutions, if we did all 12, only this one would work. So let me show you. Oh, I meant to hide that graph. So here's the shortcut. So you may have to generate on your test. You will have to generate your PQ list. Now, what you won't have to do is this. You're thinking, well, Dr. J, why'd you show us then? Well, because you need to know how to do it, right? You won't have to do this because there's a much easier way to check, and it's graphing. So if this was me, I would create my PQ list. I would not do this. So after I created my PQ list, I would then go to Desmos and I would graph this. I remember at the very beginning of this lesson, I said zeros, roots, solutions, and x-intercepts all mean the same thing. X-intercepts. So if we graph it, you can look at all of the x-intercepts on Desmos and determine really fast and really easy the solutions. Now this is a cubic, right? So our graph should make like this S shape, right? We should all know the basic shapes of graphs. X versus x squared versus x cubed. We should at least know those three. And x cubed makes an S. Now, if you notice this little S curve, right? It only crosses the x-axis at -2. So that's the reason why out of the 12 possible choices, only one of them worked. And because we're only looking for rational roots, yeah. Yeah, so some might be imaginary, some might be irrational, and that's why it doesn't show up in the list. So that list is only for possible rational solutions. It is not a complete list of all of the solutions. Only the rational solutions will show up. So by graphing it, we can see we should only have one rational solution. And that's why -2 worked over here. So the actual roots that we have, -2. What's underneath this box here? Oh yeah, this is just from the previous page. So just showing this again from the previous page. Remember, this reduces it. So we started with x cubed, so this becomes x squared, right? This is from last week. So this is 3x squared plus 1x plus 3, remainder 0. I'm just showing this here just for fun. And then the factored form, again, just for fun again, right? Just for fun, I am showing that we said -2 is a solution, and then the binomial form, just like the beginning of this lesson, the binomial will look like this, x plus 2, right? Go from the solution to the binomial form. We just flip the sign. This is why all of you should have been paying attention at the very beginning, just to see that connection. So this right here becomes x plus 2. When you reduce this polynomial by x equals -2, we get this. So that's why I wrote this right next to it, because we factored out x plus 2. Now, if you were to multiply this binomial times this trinomial, you would absolutely get back to the original problem. All right, is that clear, everyone? All right, so I am showing you a little bit more than the modules are going to show you, but I really do think this is really important to see to help you kind of understand how everything kind of fits together and works together. Okay. Right, now, this 3x squared plus x plus 3, if you wanted to go to Desmos and you wanted to graph this to see if it crosses the x-axis, to see if we have other zeros, the answer is it's not going to. I can promise you right now, if you graph this, this will create a U, a quadratic, right? But it will be floating above the x-axis at a height of at least 3. So it'll be floating somewhere up here. I don't know if it's going to be shifted left or right. I have no idea, but it will not cross the x-axis. And that's because the solutions for this have complex or imaginary solutions, and they're actually imaginary, which we're not expected to factor this in this class. At least not yet. All right. All right. How's everyone doing so far? Good. All right. This last problem, even though this is my closure problem, I do have several pages because we're going to make some other connections that I'm going to show you. So don't zone out just yet. We're going to do a little bit more with this closure problem than we did so far. We got about 15 minutes left. All right, so we have 5x cubed plus x squared minus 5x minus 1. I went ahead and I generated our PQ list. So I did the work, and we have plus or minus 1 and then plus or minus 1/5. So we have a total of 4, right? We have a total of 4. How many solutions should we find in this polynomial? 3. All right, because it's a third degree polynomial. So we should have 3 solutions at most. So we created a list of 4. So hopefully we find 3 of the 4, right? So the question here says, which one is not an actual root? So the way that I wrote this question, this question is implying that all of them but one work. Yeah, which one is not an actual root, which means the other 3 of my 4 are roots. So we must determine which one of these 4 is not a root. So everyone, I'm going to give all of you I'm going to say, I think 3 minutes should be enough. Well, it might be barely enough. 3 minutes. Calculate all of the, or check all of them with synthetic division. Ready to go. 3 minutes. Just curious, is anybody actually graphing it first? I think that's smart. I think it's good to graph it first. And then after you graph it, then verify, right? Verify mathematically. Yep. Yeah, I do want to use synthetic division, right? We need to practice, but you can graph it first just to kind of verify visually of what the answers may or may not be before you plug it in. Seeing is believing, right? All right, 3 minutes has passed. That should be enough time to find the one that does not work. So in chat, which one of these is not an actual roots? Positive 1/5. Positive 1/5. Let's take a look. And I would agree with you. Positive 1/5 is not a root. Now, hopefully you had enough time to go through the rest of them. That one works. That one works. That one works. See how we get remainder 0 every single time? That's what we should expect if all of these were solutions. Checking these, check out. This one does not. So to answer the question, not an actual root would be 1/5. 1/5. How's everyone doing so far on this problem? All right, good, good. Now, this last part I'm going to show you might just like blow your mind. So make sure you're paying attention. All right. Now, if you graphed it, which I encourage all you to graph it, you can easily see that it crosses at -1. So so -1 should work, and it does. It crosses right here, and that's going to be a fraction. So this is going to be negative something or other, right? Negative fraction. And the only choice that we have here will be negative 1/5. So that's probably negative 1/5 or negative point or 0.2. And we checked that out and that worked, right? And then we can see here that it crosses at 1, and we check that one, and that one also works. So graphically, it shows our three solutions. We check them mathematically, and it works. We can see pretty clear that it does not cross at positive 1/5. So it's clear that 1/5 probably doesn't work. It doesn't work, right? So graphically, it confirms what we found mathematically. On this page. So something that we haven't done yet. This is the bonus part, right? You can daisy chain synthetic division, and it can be beneficial, like in this case here. So let me show you. So when we do, it doesn't matter the order. You could do -1 first, +1 first. You can do the negative 1/5 first. Doesn't matter. I did -1 first. So we did the math and we got that. Everyone agree, right? And then if we were to write out the actual polynomial here, now remember, since we started at x to the third, this becomes x squared, right? So we should have 5x squared minus 4x minus 1. Okay. Make sure you're paying attention, because if you're not paying attention, you just kind of pop back in this window. You're going to be like, what happened? Pay attention. All right. So we factored out x plus 1, right? The binomial x plus 1. So we factored out x plus 1, and we're left over with 5x squared minus 4x minus 1. Again, by doing synthetic division, we factored out x plus 1. We're left over with 5x squared minus 4x minus 1. All right, is that clear? Okay, good. Next, since we know the three solutions already, we're going to daisy chain it, and we're going to do the same thing with what we just got, but now with 1. So save the fractions to the end, just because it's just easier to write. So we know that -1 works, remainder 0. We know 1 is going to work, but now instead of doing it with the original, we do it with what's left, which is 5x squared minus 4x minus 1. So 5, -4, -1. 0 doesn't come into play into this. So we do synthetic division again, and we get that, right? Drop the 5. 1 times 5 is 5. -4 plus 5 is 1. -1 times 1. Sorry, +1 times 1 is 1. -1 plus 1, remainder 0. So remember, every time we do this, we should get remainder 0 with the ones that actually work. If you don't get remainder 0, something messed up somewhere, right? So that one worked. Now, again, remember, we started with 5x squared, so this solution gets reduced by 1 power. So this becomes 5x. This is 5x plus 1, remainder 0. So I write that right there. Everyone doing good so far? And then off to the right, we now reduced this trinomial by x minus 1 factor, and we're left over with 5x plus 1. So my x plus 1 carries down. We factored out x minus 1. Remember, we always take the opposite of this to go back to binomial form. So we factored x minus 1 out of this, and we're left with 5x plus 1 binomial. All right, everyone follow along so far? All right, now the last part. Now, if you wanted to, we could say, well, we could set this equal to 0, but nah, that's going to be confusing. Let's just do it again. So we're going to now do synthetic again, but now with negative 1/5, right? So we're going to drop the 5 like we always do. We do negative 1/5 times 5 is negative 1, 1 minus 1, remainder 0. So remainder 0, that works. And we expected all three of them to work because we did it on the previous page, right? So we reduced this by a factor of negative 1/5. Well, I'm sorry, not a factor, but remember the binomial becomes x plus 1/5, right? So so this became x plus 1/5. Then we take the opposite. And then we drop that one, we drop this one. So what we have left, remember this was x squared, right? This was just x. The answer we drop by 1 power. Well, 5x to the first to 5x to the 0. Now remember, anything to the 0 exponent is 1. So basically we have x squared, x. Now we don't have any x's. We just have a constant. So this is the last piece when we factored out x plus 1/5. So that 5 is what comes out by itself. That is the only piece left. That is the fourth factor, which is just a scalar. And that's why that 5 is there, because of this. Now, let's say we got 0 right here. We got 0. Actually, we wouldn't get 0. We would get 1. If we got 1 right here, we wouldn't have to put the 1 in front because 1 times anything is, well, itself. But in the case of just getting that number always goes out in front. So now, this polynomial is completely factored by using synthetic division. If you multiplied all of this back together, you would absolutely get back to the original problem. So that is the fully factored form. Now, remember, this is bonus. You don't have to, this isn't what you have to do for this lesson, this section, but this is going to be helpful for future lessons that we actually kind of revisit, maybe something like this. But this way we were able to fully factor this using synthetic division. How cool is that? How cool is that, everyone? Your mind blown yet? I think it was super cool. Yeah. So we're going to do some really cool stuff in this class and how kind of math really kind of fits together and works together. A lot of this stuff is theoretical. Like you wouldn't actually use it in daily lives. Like you wouldn't balance your checkbook by using PQ list, but some of this is really pretty cool. Well, guys, it's 9:30, so let's call it a day. And thanks for coming. And as always, I hope you learned something. I will see you all tomorrow. I'll see you all in September.